And today,
I think you're good to start. If you already started, my bad.
Yes. Sorry, that just makes me happy. Great. So our plan for the hour is this, which is so I want to finish showing why the structure sheaf and modules make honest sheaves on Spec A, and as to why we'd want to do this. Now we're cabling that for a little bit, but I'm deliberately going to do it in slow motion and also try to sneak some fancy things in on the side. And then depending on the time, I want to begin to get to some projective geometry. And I should also say I've started to think about topics that I would think of that I'd want to talk about for the end of the pseudo course or the summer chunk of the pseudo course. That would be things that you can actually do with these things. And I've had some ideas, such as some curves and cohomology and things to jump to. But if there are other suggestions, feel free to say them, although I'll likely ignore them because likely they'll require too much. Okay, so let me remind you where we were. And now, because I need to simultaneously be able to have my mouse handy. Great. Okay, so here's where we were. So we I want to move something a bit more. Great. So we've been thinking about examples of schemes, and there's one gap that I skipped over proving last time. So we have a ring B and a module over that, which I will call N. Then, okay, some time ago, we've defined the topological space, the Zariski topology, Spec B. And on it, we have a base for the topology, which is the distinguished base. And I just want you to be have this on the tip of your tongue, that it's the distinguished base, it's the open sets are the distinguished open sets, which means that's where functions don't vanish. Or the complement of where they actually do vanish. Now, what I would want hardwired into your brains, like I feel like anytime you see D of F or V of F, you immediately think in the same thought that these are the points where the function vanishes, or these are the primes that the function is in, and that these are the identical statements, and that you can't say one without thinking of another. Okay, great. So now then we defined this pre-sheaf and twiddle, and at least the pre-sheaf on the base, and we defined it by saying that on a distinguished open set, it was going to be the localization at F. We checked, it was that was a pre-sheaf. We talked a little bit about what subtlety there was, but it's not too hard to see that it's a pre-sheaf. And then the question is, why does it form a sheaf on a distinguished base? And as soon as it does, then it defines a sheaf on Spec B. And as soon as it does that, we can define scheme. So the one thing missing is this is the sheaf axioms. And actually, we even did the identity axioms. So really, we have only one. Okay, so that's our plan. And what I'd like to do is give one or two proofs, or maybe three, depending on how you count. But the proof, I think, is really worth seeing the first time you see a proof is really hands-on, because otherwise it can look kind of formal and you have no idea where it comes from, and it really comes from something concrete. So here's what we have to do. So we have a cover of one of our open sets, and we have an open cover of it by a bunch of open sets. So I'll call the first one D of G, and the later ones are all D of G subscript stuff. And these pairwise things intersect, and we know where they intersect. They intersect in the product of two of them, because the locus where GI is not 0 and GJ is not 0, the intersection is where the product is not 0. So what do we need to check? Well, we started with our module N, and we know that we want the section over the distinguished open set to be N sub G, and over each of these smaller open sets, we know exactly what we want to. And so we want the identity and glueability axioms to hold for this open cover, every single open cover, which is a question in pure commutative algebra with rings and modules. Okay, let me take a break quickly just to get more practice with the sheaf axioms. So if we have a sheaf of abelian groups, so I want to, normally I would just say sets and then you add additional structure. For these tricks, I want to use abelian groups. And then you have an open cover, so this picture is just the same as what was on the previous page. Then the sheaf axioms can be restated as the following, which is, you want to say that the sections over open set U should be precisely the things that come from here, from the cover, that agree on the overlap. So the translation is that it's exactly those sections over the open sets that agree on the overlaps. And so you can describe it as a kernel of a map of billion groups. And that's why I need kernel, because I need a billion groups, because I need to use the word kernel. And then if you can put this in the language of exact sequences, which once you're fluent in, this is the obvious way to do it. And when you're not fluent in, it obscures things. So you want to check that this is an exact sequence of billion groups. And don't worry if you're not fluent in that yet. So I'm going to mention actually, maybe I'll say something quick about these, and these are asides. Maybe I'll put something in print, but I don't want you to be distracted by it, which is when you see this, you might want, you see this like there's some ordering, mi minus mj. And I just want to say quickly that we don't need to assume that I is less than j in case someone is getting very nervous about well ordering and crazy stuff like that. So don't worry about, so you don't need to worry about that, because you can really include I less than j and I greater than j. And you could also allow I equals j, and there's no cost. And really, if there's no benefit to you, you shouldn't check this out. You should not worry about it. But if there might be benefit to some people who realize they need to have interesting intersections of something for themselves. And then my last added statement, maybe I will not say this, because I will not write it down, because I don't want anyone to think about it if they haven't, if they're not ready to. So the sequence, you can't help but look at this and see 0, 1 open set, intersection 2 open sets. So certainly it looks like it should continue. So I guess the question is, how does the sequence of questions I might ask is, can you make it continue so it's infinite? Secondly, can you show that for a sheaf it is exact? And thirdly, then why is it that we sort of forced the problems to show exactness on a few of them, and then from then on it's for free? So something magical is going on, but we don't care for our current purposes. Okay, so now comes the next trick I want to say, which is the following thing, which is if you have, imagine that you had an open set U, and you covered it with smaller open sets, and you're curious about the sheaf axioms for that cover. And let's say you had a smaller cover, you had a subset of the open sets. In fact, you might have had 17 sets covering you, but you could actually restrict to just 4 of them, and they would also cover you. So it's a subcover. So, I would call that a subcover. And so then I want to point out essentially that, I'll say it more precisely in a sec, but if you can check the sheaf axioms for a if you know they hold for a subcover, then for sure they hold for the cover in general. Now let me say that more precisely so no one catches me in a mistake. Well, you will catch me in a mistake, but not this one. So if you have a pre-sheaf and it satisfies the identity axiom on a subcover, then it does also for the entire cover. So all I'm saying, if you parse what this says, it says that if you have 2 elements of f of u, and so I'm wondering if they're the same over each of these smaller things, then they must be the same. But if I know that they're the same in a subset of the smaller things, in fewer of the smaller things, then they must be the same, then I'm already done. Like that's all I need. So it's sort of an easier, it's a strictly weaker question. And if that weaker question, am I saying that the right way? I'm saying this horribly. So in other words, let me put it, if you have 2 sections, if you have 2 elements, you have a map of sets. And I've got this, I tell you that if I take 2 elements here and they go to the same things here, here, and here, then they must have been the same thing to begin with. Now I said, okay, let me add some more here. Then it's still going to be true. All I'm saying is you need fewer of the open sets to make it work. I said that terribly, but that's okay. And like a really simple case of this would be if the subcover, if one of the elements in your cover is the entire space. In that case, the identity axiom is cheap. If 2 things are the same, if 2 elements over the entire space restrict to the same thing when restricted to the entire space, they obviously must have been the same thing. So that's a seemingly stupid special case. And now part 2 is if you have a pre-sheaf that already satisfies the identity axiom. And then the statement is if it satisfies the glueability axiom on the subcover, then it does for the cover as well. And then that one you can think about a little bit, and maybe it's worth thinking about on your own. And I'll just say a few words about it, but not say it extremely precisely, since I already confused myself with the identity axiom. That if you have, let me draw a picture of a cover, and then the pairwise covers, the pairwise intersections. And so in this case, you're given sections over each of these open sets, and you know that they agree on the pairwise overlaps, and you're wondering if they come from something here. Well, if you already know that it works when you consider only a subcover, that in this case, it comes from something here, then it sounds great. Already you can glue these together. But now the only worry is that maybe when you glue them together, they get something on the total space, and you restrict it to one of your bonus guys, you might worry that you may get something different. And then if you parse what that means, that's the identity axiom. Okay, so that's a complicated way to say something which is maybe not super simple, but is not actually too bad. So to say it again, if you have a subcover that is where it's a sheaf, then basically you know the entire thing's a sheaf. Okay, so let me go back to the picture and get more concrete. Okay, so our question is about the following thing. So if you have a subcover, a subdistinguished cover, and so the subdistinguished cover means the subdistinguished cover means, actually, let me take a quick check to see whether I should have done something earlier. Actually, there is something I meant to do earlier, so forgive me while I go back and say that what we wanted to do back here, this was in order to, what we're trying to prove is given any distinguished open, and then any cover by smaller distinguished opens, then blah, 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 blah. And then I wrote it down in algebra. And now I can just point out that if I call M n sub G, and I call A B sub G, and then what I've done is I've replaced, this now looks like AG1, AG2, sorry, MG1, MG2. So so you can quickly reduce, and I have this as an exercise in the notes, from the case where the distinguished open set is not everything to the case where it is everything, and that makes life easier. So so our question is this: so we have a bunch of distinguished open sets whose union is everything. Then we want to show that they satisfy the sheaf axioms. And now the thing that I hope you cannot stop yourself from doing, whenever you see this one statement of a bunch of distinguished open sets being everything, you should immediately say that that's the same as the ideal generated by things should be the unit ideal. And then whenever you see that, you should immediately say that this means that there's some combination of these things, which is one. I should put one in brackets there, I'll call it A. And this is for some elements of your ring. And for this to make sense, this means all but finally many are zero, because you don't know how to make infinite sums in general rings. And just to be clear, that's what this ideal are things of this form. The ideal generated by dimensional ones are things of this form. So, so that means that in fact there's a finite sum of only some of them. That's one. And that means that if you go all the way back through, it means that there's a finite union of that cover everything. And the great thing then is by the subcover trick, if you do, and I should say in the notes I said it differently if you don't like the subcover trick, if you can do this finite cover case, then you win. So our goal now is to show that if you have a bunch of things that generate the unit ideal, or translation, the distinguished open sets cover everything, you want to show that any module is the kernel of this map of localization to the double localizations. So, okay, let's do the identity axiom, which I did do last week. So if you have, an element in this, so if you have an element of your module, and you know that it's zero in every one of these localizations, the question is, why is it zero? Why was it initially zero? But whenever you have something in a localization, by definition, which means you can't help but write it down, this is a statement of something in capital M, which says that some power of f times m is zero for some power of f. But that means that m, which is 1 times m, or 1 to any power times m, you could take this description of 1, take it to a huge power, and in every monomial, you're going to have one of the fi to the bi's is going to appear. And that means that when you expand it all out, you get that it equals to 0. So m is equal to 0. So that's what we did last time. And now let's do the concrete thing, which I'm hoping will be believable and comfortable to understand. And so here's what we need to do. We have a bunch of open sets. These open sets are the form d of fi. There's one of them, there's another one. And then you have these pairwise intersections. And we want to say that if we got a section over, over each one of these open sets, in other words, we have an element of each of these localized modules, and they agree on the overlap, then they must come from, we're trying to find something that they glue to, some element, some section over the entire spec A, in other words, an element of the original module. So that's the game we have to play. Given one of these, basically for every value of 1, for each open set, and this fact that they agree, find m that equals each of these in the various localizations. So let me just make a bunch of reductions that are hopefully all reasonable. That the first reduction I'm going to do is I'm just going to rename f1 to the L1 to, let's call it G1. And that's okay because the locus where f1 doesn't vanish is the same locus where g1 doesn't vanish, or the localization by f1 is the same as the localization by g1. So all I've done is I've made my life simpler by getting rid of those exponents. And so I do the same thing here. And now the fact that these two agree on the overlap, so I have these new terms that are just renaming the old ones. What does it mean for them to agree in the overlap? It means their difference is 0. Well, what does that mean? I can state that in terms of my original module by saying that this minus this, and I clear the denominators, times some power of, the overlap is d of g1, g2, times some power of g1, g2, times this is 0. So I'm just restating the fact that they agree. But now, there are finally many overlaps. So I've got these some number up here for every pairwise intersection. So I might as well just take an even bigger number and have it just a single big number that works for all pairwise overlaps. So now at this point, we have, this is now just some number k like that. Okay, and so let me just write down here that gi was fi to the li, and d of gi was therefore d of fi. And now what I'll do is I'm just going to instead multiply the top and bottom of these fractions. So I'll just write down what I'm going to do. That I'm going to let ni be, I'm going to multiply the top and bottom of this by g1 to the k. So gi, let me say this like this. So so when I do that, this thing turns into n1 over h1. n1 over h1 is indeed m1 over g1. So all I did was rename them. But the advantage of that renaming is this thing here turns, this k term disappears. It gets sucked into what we wrote in. So in other words, that means that we now have this very simple situation that for I equals 1 to n, we have this elements n1 over n1 and h1. And the hi generate the unit ideal, and we know that they agree in the overlap. So hi and j equals hj and I. So now we're ready for the restated question. And all I'm doing is restating the question, which is that the hi generate unit ideal. Translation, the d of h's, which are just the d of g's, which are just the d of f's, they generate the unit, they cover spec A. And so we have, furthermore, we have these n's as well, such that this fact is true. Hj and I equals hi and j. So I'm now going to finally tell you the thing tell you how they glue together and what they glue together too. Let me just define m to be the sum of bi and I, which looks a little bit like the sum of the bi hi. And now the claim is that this works. So I claim that in fact, m is n1 over h1 in this localization. And now let me prove that it's true. What do I need to do? I need to show that h1 m1 minus n1 should be 0. I guess I should also put some big power of h1 here, but I don't even need to do that because of how I cook things up. So let me make this more readable. Great, but I said that m was this thing here. So I have h1 times bi ni, that sum, minus n1. but H1 times BI is equal to HI times B1 by our gluing condition. And now I can take out the, no, I screwed that up. Sorry. Okay, so let me see what I've done. Great, so M is equal to the sum of BI and I, and there's an H1 there. And we know H1 and I is HI and 1. But now the sum of BI HI was 1. See that? So I get 0. So it just works. So all that happened, I mean, I guess it looks a little bit like magic, and if it looks like magic, then that means there's some structural thing going underneath. And there's a reason why Sarah has called this a partition of unity argument, and if you squint, this might be one. But at the very worst, you could perhaps believe that I just followed my nose and was just a little bit careful, and it just works. And maybe it's a mystery as to why it works. And so that means we are done. We have proved what we wanted to prove. So I should always remember to keep updating, and I keep forgetting. Okay, so now you know it's true, and I'm going to deliberately probably waste all of our times by giving another proof, which I find to be enlightening, but maybe only to people who are already enlightened. So this is maybe less value, but it can be enlightening to people who are not super duper enlightened and only a little bit enlightened. So if you're on your journey to enlightenment, then this may take you several steps along it. Okay, great. So here's what we wanted to do. If you we're trying to show that this thing is exact, in other words, where the FIs generate the unit ideal and M is any module. That's our game. And so so now here comes the one algebra fact I want to use, that this is to check whether something is exact, you just need to check that it's true after you localize at each of the FIs. So that's where the algebra magic happened. And this is where you use that the FIs generate the unit ideal. So just to be really clear on what you have to prove to make this work, and this is just a very fundamental fact, so at some point in your life, if you go further with this, you will prove it, or you will see the proof of it. It's the statement that if you have a sequence and you're wondering whether it's exact, you can check whether it's exact after localizing at a bunch of elements spanning the unit ideal. And now what really is going on there, it's that you could capture the failure of exactness by this thing called homology, which is literally the failure of exactness. And all the constructions you make behave well with respect to localization, and of course, doing that computation. And so if the homology module is non-zero, then it's gonna be non-zero after localizing one of these FIs. And then if you're a couple steps further on, you realize that then what we're really using is faithful flatness. And I'm not going to say what that is, although the word will come up again. And then that's the, okay, so then we want to check. Let me go back to the question. We want to check if this is exact. And it suffices to check it after localizing at each one of these. So for each FK, I want to localize. In other words, I want to localize at FK. So I just wrote down the same thing and I put an FK in the denominators. I want to show that that's exact. And now I just want to observe, this is an exact, I could say it's an exact sequence of A module or abelian groups, it doesn't really matter. But so I'll say just abelian groups, not A modules, because if I take a new ring, which is a localization of F sub K, and then new modules, which are the localization of F sub K, because we're living in a world where FK is invertible, then if I change my notation to this new notation, I want to show that this thing is exact. I've got B modules, and I've got N and this, and the FIs, again, still generate the unit ideal. So that's great. That's what we want to show. And now you're probably sad because it's exactly the same thing as we started off wanting to show, just with a different ring. But you should not be sad, because in this cover, you see D of FK. But this is in the ring A sub FK. So FK is a unit, and this is everything. This is all of spec B. In other words, one thing in the cover is everything. And by the subcover trick, as soon as you have a stupid thing in the cover where you know glueability and identity, then you know it all is. So that is a proof by magic wand And then you take the magic wand and you shrink it and you make it disappear too. And now the argument gets simpler and simpler, but it's less and less motivated. So I feel this is going to be useful for fewer and fewer people. But let me just say it anyway, so you can see the number of words shrink to 0. So if you have, so now we have an A module, and I'm going to say something. I'm going to give you some questions. I won't even tell you why they're true, but there's something you can do if you are ready to reach this stage in your journey. That is, so if you have an A algebra, and we're going to show that under some hypotheses, M to M tensor B to M tensor B tensor B is going to be exact, and the maps look like this. And if you, the thing to have in mind is where B is the product of each of these rings, or one of these rings. Okay, so and then these maps are exactly the maps you're expecting, given what we just did. So the first problem is to show that's exact if A is B, if A equals B, and that's just the trick that let us finish off the problem last time. But then if you pay attention to your trick, you realize you don't need A equal to B. All you really use is the fact that there's a section from B to A. So we have a map from A to B, and we need a map from B. If we have a map from B to A, so that's, let's see, let me zoom in so you can see what I wrote. There's B, A. So we already had a map from A to B. If there's a map from B to A, so that, make sure I have all this the right way. So we have a map from A to B, and we want a map from B to A. And I feel like I hope I haven't done something stupid. So that it commutes. So all that matters, you need that map from B to A, which will give you a chance to give you maps like this, for example. And so if you just take the same argument and look at what you did to make it work and realize that's all you use, then you can prove part B. Okay, so then the third final variant of this is that if B is faithfully flat, and I will now tell you what that is, which is that a faithfully flat is just the thing which is designed so that to check if an exact sequence is something exact, it suffices to check after tensoring with the ring. So this is exactly what I mentioned earlier, just in different words. And so in that, so the claim again is that this thing is exact if and only if, not if and only if B is faithfully flat over A. And here is, so how does the proof have to go? Well, we need to check that the star is exact. So, and the only point of having it faithfully flat is, the only reason for that hypothesis is that you know what I'm about to do is to tensor it with B. And when I do that, I get this, which looks awfully suggestive, but I need to tell you what to do next, the right hint for what to do next. Now I'm going to give you a new ring, A prime, and a new module, a new B prime, and a new M prime. And my new A prime is going to be B. My new B prime is B tensor B over A. And my new M prime is M tensor B. Now, why did I do this? It's so I could make the first term look like that first term, this term look like that, the second term match that, and the third term match that. So now I want to show that this is exact, and I might as well rewrite it like this. And what did I gain? What I gained is there is now a section, B prime to A prime, that sends B1 tensor B2 to B1 B2. So cheaply, there is a section, and then you win. And if you squint, it's exactly the same argument we just did. So there's no difference at all. Okay, so what have I done? So far, all I seem to have done is take the argument that already worked and just observe what made it work and give the same proof. So there's no extra, nothing very exciting that seems to happen, but we've just proved flat descent. This is for people who know what descent is. This is flat descent. And for people who don't know what descent is, this is flat descent. So the statement and the proof were complete once you do those couple of exercises. Well, okay, but forget that. Almost everyone should just forget I said that. But the point is just that later on, when people say descent, all they mean is gluing. Okay, so a couple just loose ends to tie up, which is the structure sheaf on Spec A. I can tell you about its Stalks, and the Stalks are just the localizations of A at P. And similarly, if M is an A module, you have the sheaf M twiddle, its stalks are just the localization of the module P. And this is not rocket science. I mean, it's fancy if you, it would have been fancy, but you basically told me the reason we made the definition of a locally ring space was to make this true. The Zariski topology came from this. So if you parse what this means and you take the limit over all neighborhoods of the point, or all, if you want, distinguished affine neighborhoods of the point, that involves putting more and more things in the denominator. So just think about it and you realize that you were forced to this by what you told me before. Okay, so that means, so now the fact that M twiddle is a sheaf has consequences, which are, so let me say something, which you could check in other ways. But one thing you know is that if you have a sheaf and you have an element, a section of the sheaf that is 0 in every stalk, then it must have been 0. So let's just apply it in this case. What this means is that if you have, so the sheaf is going to be M twiddle. If you have a global section of the sheaf, M, and it's 0, it has 0 germ everywhere, then it must have been 0. That's just sheaves. And now that's an algebra statement too. So you can prove the algebra statement, and depending on who you are, you'll like the sheafy version of the algebra statement too. Similarly, then, if all the elements of a module are 0, it must have been 0. So the similar thing is that a module is 0 if and only if all of its localizations are 0. This may again this might remind you of my statement about you can check homology or exactness by localizing. Okay, so another a useful definition is that if we have a locally ring space, and you have an O module, like think M twiddle in our example, then I can define the fiber of it at a point, and I will try to give some geometric motivation in just a second for it. So you take the fiber, which is F, I should say F sub P, and F sub P is a module, is an O sub P module. So F sub P mod MP FP is a module over the residue field. So what we have is that just like the value, we have the notion of a value at a function at a point for a locally ring space. Similarly, for any O module, we get a vector space. For every point. So that means we can now at least begin to picture modules over rings, because now first we start off on picturing our rings. So spec A is some sort of space. And now if we have a module, we build the geometric thing. And it's something which to every point of spec A, now we have the data of a vector space over that field. So we have a vector space over every point. And that contains important information about the module. Yeah, and so this is suggestive in so many ways that class groups are really geometry, vector bundles. You might think should have an algebraic meaning. Commutative algebra gets mixed in there as well, and so that's now that's worth. Yeah, so you can see the beginning of something coming together. And another stock related thing is that at non-closed points, I just want to make an algebra statement, which I think you may not realize automatically. So at the non-closed points, given a prime ideal, if you want to work out what the stock is of the structure sheaf, well, you know what it's going to be, and you can get there by either quotienting and then localizing, or by localizing and then quotienting, and the order doesn't matter. And I'll let you think about the picture. But similarly, you could do the same thing with a module. You do the same thing with the module, so you have without any change. The main point is that quotient localizing, you can do it in either order, so you do whatever is easiest in this situation. Okay, so at this point we fully know what schemes are. We've got the sheaf. We mostly know what varieties are. We know it's a ring space that locally looks like something that we've made friends with. And so one useful tip for gluing schemes, which I will leave as, well, partially as an exercise, but I will give you most of the idea right now, is that how do you build a scheme? Like how do you build a manifold? You can glue together lots of local patches. And a useful thing for schemes is you can take a bunch of schemes and glue them together. And what you need to glue them together, rather than taking something and recognizing the open cover in it, instead you want to begin with the open cover and figure out how to glue them together. And the information you need is you need to know things up to triple overlaps, not less, not more. And so let me now say this in terms of gluing ring spaces. So this says schemes, but really this is all about gluing ring spaces. And so if you have a bunch of ring spaces, now in particular, I want to also glue infinitely many. I don't need, I want to be able to do something rather serious and glue together lots and lots of things. And so I've a bunch of things, not even countable in case you are anal about that. I just don't know how to easily write an infinite number of things. So given a bunch of ring spaces, and I want to glue them together under by open sets. So I'm going to glue xi to xj by taking an open set. Oops, that's wrong. Xij is inside x sub I. And so you have an open set of xi and an open set of xj, and you want to glue them together. So you have these isomorphisms under which you're going to glue them. But you don't, but you want the triple, you want, when you glue I to j and j to k and k to I, you want that to not contradict itself. You want it to be its identity. And so I guess I should say, you have to say what that means. What does that mean? And this is so this is a co-cycle condition. This is something which is on x, an open subset of x sub I, that says that you have no contradiction of gluing them. So once it satisfies that, then you can glue. So the question is to show that there's some x with an open cover that is the thing that glues together this data. And I guess you need to know what that means. And the resulting thing is unique up to unique isomorphism. You can say what that means. And the one thing I want to say is that whenever anyone hears this, the first way to think about this is you first think, okay, I'll prove it by induction. And induction does not work for infinite, if it's infinite cover. So induction cannot be the tool. So how do you get a hold of this? Well, the answer is a ring space. You don't think of it as just a ring space. It's a set with a topology and a sheaf of rings. And you already know how to glue together infinitely many sets. And you already know that given, so that's, and you already know what you need to do to make sure that the topologies agree, and that's the triple intersection. And then with that, the only question, once you built your glued topological space, the question is, what is your sheaf on it? And that's not so bad, because to know sections of a sheaf on an open set, you just need to know it locally. You just need to know it on each of the xi's. So somehow so anyway, I'll leave you to think about that. But it's useful and important, because then with projective space, it makes it easier to, you have to glue together. Pn is going to have a bunch of open sets, and you don't want to get confused with what you need to know as to whether they glue together. Okay, so now we can get concrete. And so let me just say some things that we can define immediately. And so let me first define, just as an example, in P2, here's an equation for you. And I want to point out that this is a homogeneous polynomial. And this means that the total degree of every term is the same, is the degree, which is called 2. Okay, so let me define it, and you will see in the course of doing this why we need homogeneity. And so let me just remind you of our conventions for coordinates on P2. So what does this even mean? Well, that's why we have the problem to define it. So on U0, well, there the ring was generated by x10 and x20, and on U1 it would be x01 and x21. And there's a way of communicating between these two rings, which said, for example, x01 is 1 over x10, and x20 is equal to x2 over 1 divided by x0 over 1. So we have this way of communicating between them. And now let me just tell you what I will now describe what this mystery thing is on each of these open sets. On this set, it is nothing more than 1 plus x10 squared equals x10, x20. And on U1, I'm going to essentially clear out the x1 squared. I get x01 squared plus 1 equals x2 over x1. So what I want to do is just have you observe. This is my definition by example. How I got from there to here, where all I did is so I don't know what x0 is. It has no meaning currently at all in P2. It's not a function, but these things have meaning inside this open set, and ditto here. So I've got this thing inside here, this thing inside here, and how do I glue them together? I already know how to get them together, and it works. So you can check that it works, and it's worth checking once, and then you realize that it's just automatically that it's extremely cheap, that they can all glue together. And so more generally, if you have any bunch of homogeneous polynomials, you could define a corresponding scheme, projective scheme. So let me just, as an example, in P3, let me do something which I'll describe in a weird way, which is consider, so here implicitly my 4 variables for P3 are W, X, Y, Z. So I'm deliberately pointing out that you may use different names for the variables. And so the locus for the rank is 1. Well, what does that mean? It means that these 2x2 determinants are 0. Whoops, minus x wy minus x squared, wz minus xy is 0, and xz minus y squared is 0. So those are my equations, and they're all homogeneous, of course. And I claim that they just cut out something inside P3. And if you want, you can see what they are in each of the homogeneous pieces, and now you can think through why that works. And the picture in my mind is there's P3. You might say, why is P3 look like that? Well, that's a good question. Maybe it's highly symmetric. Sure, it's like kind of spherical, and it's 3-dimensional. I guess that's, okay, that was 2-dimensional. That's the closest I could get to drawing it. Or maybe, no, actually it's the inside of the sphere. There we go. So there's P3. That's a good picture of it. And then, but what is this thing? It's kind of by a bunch of equations in each of the standard opens. So the resulting thing should be sitting inside P3. And it turns out to be a curve, not that we know what that is. And this is a twisted cubic curve, whatever that is. So we don't know what, I don't know what twisted is. You don't know what cubic is, and you don't know what curve is. So, okay. And so more generally, we can have the construction I want to do next week, or possibly I will just give, I think I actually want to do this one, that given a graded ring. Now, what do I mean by graded ring? It's a ring with a gradient. What do I mean by that? If you think about it a bit, you'll be led to the correct, approximately the correct definition. So an example in the case we just looked at of the twisted cubic, the graded ring, the first graded ring to get projective space was this graded ring in 4 variables. But now instead, we're going to just impose those equations, and still any polynomial in here mod this, the pieces have well-defined degrees. And so to this, I want to get a scheme or variety. Maybe I should have said everything we're talking about works just fine with varieties as well as schemes. And for example, when you apply the construction to this example, you should get what you already have done in an example. And so that's what will come. And then you should expect that maps of rings should give maps of projective schemes in the opposite direction. Sorry, maps of graded rings. So maps of rings give maps of affine schemes in the opposite direction. Maps of graded rings should, I'm actually lying, but it'll be very clear later why. It's a very natural, it's clear to see why it has to be a lie and how to get around it. So maps of graded rings should give maps of projective schemes in the opposite direction. And so as an example, if you take the polynomial ring and you mod out by this ideal, that's a map of graded rings. It preserves what, in any reasonable definition, a map of graded rings, it has to be preserve the grading. So this projection of graded rings will turn out to be the picture on the previous page of this twisted cubic curve mapping into P3. And I guess one thing which is not yet clear, this twisted cubic curve is secretly P1, is isomorphic to P1. And so what do I mean by that? I guess at this point, we can, I should have said it back here, that what we're describing turns out to be equal to P1. And we don't know what morphisms are of schemes or varieties, but we do know what isomorphisms of ring spaces are. So this has a very reasonable, this is a precise question. Something that you can prove without needing to wave your hands about what a definition is, which is you have this thing P1, which is a ring space. You have this thing from the previous page, which I didn't formally do, where I didn't formally say what the recipe was, but you will define something and it will be P1, and you can match up the rings in topology. And that is an interesting question to do given what you know, because you are somehow doing it with both hands tied behind your back. You can really do it. And in the course of doing it, what you'll figure out is like, where do the points of P1 go to? Well, every point in P1 has to give you something in P3 space. Actually, let me give you one hint, which is that, let me say something, let me get this here, which is there's this P1 and there's this thing inside P3. And I'm going to say things that have no meaning for you, that I've not defined yet it will help you answer the question that has a precise meaning. So what's a point in P1? It's like an ordered pair up to scalars. Let me put in square brackets to suggest that it's no, it's that it's not like just an ordered pair, where you're allowed to multiply it by scalars. And when you, where does this point in P1 go to in P3? I will tell you. And when you see this, it looks very suggestive as well, and you'll feel like this is a special case of something much more general. That's true. Okay, so now let me tell you, actually there's some I will say now because happily, happily I thought I would get here 5 minutes later than right now, that now we can talk about properties of varieties and schemes. Some of them are quite, are cheap and easy, and others are, actually they're all easy. Some are just require something very sneaky. And like I think the highlight for me is this way of communicating between affines that's called the affine communication level. So let me take care of the topological aspects right now because because there's not too much to say, at least immediately, that topologically you can now extend all the notions before, such as connected, irreducible. So a scheme is or a variety is a topological space. So you can define quasi-compact. And now I have to remember if there's more that I want to say quickly. And so those are like those are the basic ones. I can talk about irreducible components, connected components. And then there's the idea of a Noetherian topological space. And the meaning of this, or the reason for this, is that there should be finitely many pieces. Right now we have a phrase. Now we know what this means more precisely. Finitely many irreducible components. So it implies, not equivalent to, finitely many irreducible components. So I will say right now some things in words that pictures would lead you to expect, which is if you have any quasi-compact scheme where you take spec of a Noetherian ring. So each Noetherian ring is a Noetherian topological space. And if you glue together finitely many of them, so that's the quasi-compactness condition, then if these things have finitely many pieces, and that one, this has finitely many pieces, and this does too, and this does too, and this does too, you should expect the union to as well, and that should be true. And then more generally, then you should expect that a finite union of Noetherian topological spaces should be Noetherian, and so projective space should be connected, irreducible, quasi-compact, and Noetherian, for example. So this is just, there's no rocket science here. You're just doing this in the same terms, the same words to mean the same things. And the one additional thing which comes up, which is also true, which is worth saying, is that you continue to have irreducible closed subsets will correspond to points. Oh, we're talking about, this is the one of the few times when I'm talking about schemes, not varieties. Varieties, well, have only the closed points of the schemes. And so from every point, you get an irreducible closed subset by taking its closure, and conversely, every irreducible closed subset has a generic point. It's a point that it is a unique one, that is its closure. So that all these, so the topological aspects are completely the same. And now there's one last topological fact, property, which is a surprising one, which I'm not going to get into right now, and it's the notion of dimension. And so this will be the hand-wavy thing I will end today's pseudo lecture on, which is dimension is actually a topological notion. The way in which the dimension of a variety or scheme will eventually be defined the correct definition in any reasonable sense, I think, has to be topological or homological or categorical. And this may seem bizarre, but then I will ask you the following thought experiment or thought question. Well, the first thing I'll observe is that the definition, that dimension, the notion of dimension is always a hard definition. And you just forget that. Intuitively, it's really easy. You can look at something and say, oh, yeah, that's clearly dimension 2. But precisely defining a dimension is never easy. And you may say, what do you mean? Vector spaces, that's really easy. But then you've forgotten that when you first learned linear algebra, dimension, that definition is a bizarre definition. You define linear independence and spanning sets and blah, blah, blah. It's not a natural definition. You only think it's natural because you've digested it. And so the thought question I want to ask is, if you have two manifolds, how can you tell, or if you have one manifold, and I only give it to you as a topological space, how do you know how do you know what its dimension is? Or to put it differently, I could even give it to you as a ring space. And I could say, how do you know what its dimension is? And you might say, oh, good, you just cover it with things that locally look like R2, like balls in R2. But maybe you can cover it with, at the same time, with things that look like balls in R5. So why can you not do that? So make up a proof. And I ask the question because there's not one single proof. There are many things you can do, and somehow every single one leads you to topology. And it's kind of surprising. It's not nothing to do with manifolds. It's really a purely topological notion. And so in the end, dimension is purely topological, but it's subtle, and so we're not going to talk about it. So next week, or not talk about it anytime soon. So next week, we'll talk about more properties, varieties, and schemes. And I think at that point, all that's left, we wanted to talk about morphisms, and that may take a week after that. But after that, we just know the category, if you want, of schemes and varieties, and we just do stuff with it. And so all of the fundamental things, well, I guess maybe for line bundles and vector bundles, which should come soon, you're ready to just do anything with, and then maybe we'll do stuff. We'll take these ideas out for a ride and see what they can do. So that's probably a good spot on which to end for the week. So I will pause for a bit and then then we'll do the question period for the next 30 minutes or so, depending on how many questions people have. Well, I'll pause now to give a good time for me to cut this when I slice and dice it from YouTube. Great, cool. So should we go to questions? I'm gonna also put on a fan, which unless it is really bad for sound because it's quite hot. It's quite hot here, probably quite hot everywhere, at least in different parts of the US. Good, let's go for it.
All right.
You're back in our time zone?
I'm back in your time, but and then I need to look at the questions.
Yeah.
So I wrote down a bunch of topics that were coming up.
Yeah.
But let me see if there's specific ones now.
I see him. Felipe Montero has a good question. Yes, for number field. Yes. Dimension always a topological notion. I will say yes.
So yeah.
Okay.
So one thing was that, like, local properties came up a bit. Like one thing that I wrote down that I think would be interesting to talk about was, you know, the relation between flat, locally free, and projective.
Yeah. That may best wait
For another topic.
Because then we want modules. At this point, we
okay, you're gonna have a whole modules talk. Okay.
So right now,
just think about.
So maybe the word I will say, the words I've not said, although it may, people who know about them may think I've said them because it's implicit enough, but it's a notion of a quasi-coherent sheaf, which is basically, so what's a quasi-coherent sheaf? It's an OX module that locally looks like M tilde. So but we have that, to make that precise requires just a little bit of thought. But then once you do, you can start to think about you can really start to think about modules in a geometric way. And then questions of local freeness feels like it's about geometry. Projective feels like it's about algebra. And flat is this, flat lives in a whole different plane of existence.
Yeah. Yeah. So another question was, why is flat called flat?
Ah.
And so what's
not a, I've no hold on a sec to make sure. Is my sharing still going? I hit a button by mistake. Looks like it might be.
I mean, I see your sharing still going. I mean, you have a blank screen
so,
right there.
So flat. So the thing about flatness is this was, the word is from, I'm 90% sure it was from Sayre, and I'm 90% sure these are not independent probabilities. I'm also 90% sure this was from his Gaga papers, the first time this notion, this word appeared. It didn't even appear there because it was in French. But I can answer where I can sort of answer where it came from, but I also feel that it's not a great word in retrospect either. And in this case, whenever Sayre makes up a word, he tends to be right. So, and in this case, it's not his fault because he invented this thing for one purpose. And I gather, I'd heard from, this is from Brian Conrad, who heard it from Sayre, that he had this sense that this notion would be extremely powerful and useful, but he didn't know exactly how when he introduced it. And he was, as Sayre tends to be, he was completely right. And so it is useful for so many different things, and you wouldn't guess it because it simultaneously is useful in very different part, from geometry to algebra to, like, in many different ways. Whenever you say what is a nice, one question which came up in the first week is when you want a moduli space of something, you need to have the notion of what's a nice family of somethings. And the word flat has to be inside there. And the word flat appearing in this descent has to be there too. So I would my secret word for flat is exact. Like an exact module is when I see flat module, I think exact module, because tensoring with it is exact. And whenever I see what's an exact morphism, I might use that for flat. I might, that should mean flat morphism, because I think all the use of flatness, a very central part of it comes out of that one thing. So, but don't tell anyone I said that. That's not, I mean, some things I feel like there's some notation language that should change, and other things are just my secret things I say in the back of my head that.
Yeah. So I said a little bit about what a blow up, like that the fibers of a flat map are not flat, or, literally. Like,
right. I don't think that was Sayre's picture, but that's true.
I bet he probably must have had something else in mind, huh?
But he also was, I mean, I think he was not, like, here's a parabola, and it looks like this because it's over the complex numbers. And this thing looks like you might think of as a nice cover in general, but over 0, this is like x equals y squared, and this is the x-axis. You might say that this looks like a nice map. It's locally a product, except here, but it is flat. So it is, it's not naively nice, but it really is nice. And there, I don't know why the word flat necessarily, you might say that what do I want to say without, that's appropriate for this audience, that the number of points in every fiber is 2 once you count correctly. And so that's a sign of it being nice. And so, this is not the same as a covering space, but it's something which is kind of like algebraically locally a covering space in some sense, but it really doesn't, like, I feel like there's no single metaphor that captures it. But it is true that if you have a flat family, then like a flat coherent sheet,
maybe we should say something about what do we mean by a map, like, so even for rings, like, so we've been talking about flat modules, right? And so how do we apply this module definition to rings is maybe.
So, I carefully wasn't saying that because you don't know what a morphism yet is. You don't really know what at this point, all we've done, well, I can say this quickly right now.
You can do from spec A to spec B.
Yeah.
I guess. Yeah.
Right. But then you need to say the data of spec A to spec B. I guess my first terrible definition is I say, oh yes, they're just the same as ring maps from B to A. That's horrible because that gives no insight, although it's true. We do know that induces, B to A induces a continuous map. But I haven't said what it does on sheaves yet. And really, it would take me a few minutes to say correctly. On global sections, it's somewhat clear. You take functions on spec B and you want to pull them back to get a function on spec A, well, great, you know what to do. And then you might say, well, great, on a distinguished open here, when a function doesn't vanish, it'll be pulled back to something where the function doesn't vanish. And I know what that should be, and you'd be right. But then pretty soon you define morphisms. So I think I want to duck that for a little bit as to what, but I will say that, well, we don't know what dimension is, and I feel comfortable talking about that in a sentence. So in any nice family, things behave well, like Euler characteristics. That's the really big thing which behaves nicely. A dimension, anything that after a while you learn to look at something and say, that's definitely flat. That's definitely not flat. And
yeah, and I just wanted to point out that A in that example is a B module, and that's
yes.
like how we're applying the.
Oh, that's a good point. Right, that's a good thing to say. That in this case, this map B to A is a B algebra, but it's also B module. And the B moduleness is all you need for the flatness. You don't care about multiplication by elements of it.
Yeah.
Another thing I'll say is that if you have you might wonder what a vector bundle looks like. Now that if you have an M twiddle, that should be a vector bundle. I haven't defined anything. What could this possibly mean? I could say that if my ring is A, so this is spec A, you might believe that the module A plus A should be a trivial rank 2 vector bundle. But what about one that's actually bendy? And this relates to Taylor's slightly earlier question. Well, if it's a finitely generated module, that's going to correspond to finite rank vector bundle, and it's flat. Well, probably I need to be a little bit careful with Noetherian hypotheses now. So I'll toss in Noetherian just to.
Oh yeah.
But then, but if it's otherwise finally presented or where I'm not going to worry about it. Everything's Noetherian for this example. Then flat means it's a vector bundle. Not flat means it's not a vector bundle. So that's a good sign of flat being nice.
A request to update your notes, Ravi.
Oh, thank you. I keep forgetting.
I remember this quote somewhere in Mumford. He says, the geometric meaning of flatness is not so clear, but it turns out to be the answer to many prayers.
Yes, that is true.
I love this idea that you don't know what your prayers are yet, but flatness will be the answer.
And the amazing thing is after this happens a few times, then later on you're praying for something. Then you say, okay, I know the answer has to be flatness. And you're right. It's it's a miracle. It's flat does not, I wish I could know why. I don't think it's possible to have guessed flatness would be so important, or else it would have been invented before Serre. I mean, it would have been realized before Serre.
Yeah. So people were asking if this had anything to do with curvature.
No, that's another good reason for the dumbness of the name. So I think the curvature use of flatness is intuitive and well established.
Yeah, and there's a notion of flat connection that's related to, that has nothing to do with this, right? Which is
someone in the chat had a nice line about the absence of torsion being relevant to both.
That is like that's okay. That's the most sophisticated mathematical joke I may ever have heard, actually. Okay. Flatness is who made that joke? I have to find out who's what kind of twisted mind would come up with that. It's
Richard Danner. I don't know who that is.
Yeah, he's UVM. Yeah.
That's okay. That was very. I'm impressed. That's fantastic.
All right. So one thing that you were talking about, and I actually don't know if these are exercises, but I did have like what is a Veronese or what's a diuple, to give more examples.
Sure. Okay. So I will answer in the language that we currently know, which means it can't be fully precise just yet, but it's going to. So maybe as a warm up, I do want to say one thing, which is you might remember that when we have a ring map from B to A, so as we just seconds ago were talking about, this induces maps of the topological maps like this. But later, once you know what a map of a scheme or variety is, we'll get maps of schemes. But if you remember, the topological map or even the set map was really something down to earth. Like if you're used to in coordinates sending like x, y goes to x cubed comma y plus x comma x to the 19th y, the ring map would send called, I need new letters, A, B, C, would send A to x cubed, B to y plus x, and C to x 19th y. So the point is that the naive thing you're doing with sending points does tell you what's going on with the algebra. It just, you have to get used to just reversing arrows and realizing you're saying the same thing. So here's what the Veronese is, which is it's a way of taking n space and sticking it in a bigger projective n space. Okay, and you may say, why do you want to do that? And I'll hold on a sec and I'll try to justify it. But basically what I want to do is I want to take x naught through xn on projective space. And I'm just thinking naively, I'm not going to say anything. So it's an n plus 1 tuple, only well defined up to scalars. And now I'll send it to, well, let me just list all the degree D monomials in the xi's. And how many are there? It's some beautiful combinatorial thing you can figure out, which I'm not going to remember off the top. I'll get wrong if I try to say it. So I will tell you the first one, it's x naught to the D. And I'll tell you the last one, it's x n to the D. And then you can fill in everything in between. And so this map will send you to some subset of projective space. And your intuition should be, if you're thinking, that it should be that it's a closed subset. That you may have that intuition that it should be closed. And that means it should be cut out by a bunch of equations. And so, but the image is the thing which is called the Veronese, the Dietz Veronese. Why would you do it? Well, this is sort of, it's like one of these useful, it's a useful crutch to do many things. So maybe it's hard to pick the single best thing that I would pick, but maybe as one example, it's often easy to do things by slicing with hyperplanes, because hyperplanes, that's like linear, that's always very easy. But if you can slice the Veronese with hyperplane, a random hyperplane here is a random linear combination of degree D monomials. So you're going to get all the degree D polynomials. So suddenly you can slice by higher degree things as well. But it's more that this comes up. This is like a tool more than an object of study. Although then it becomes an object of study because you realize that it's intrinsic. The equations, we don't, I think in some interesting ways, we do not understand fully the equations of it. I really mean higher equations. This is a genius, but I think there's like lots of structure that is only now beginning to be understood. And I'm thinking of, well, I don't want to start to give names, but in terms of people I've worked with, Andrew Snowden at Michigan, or Stephen Sam at San Diego, or Jan Dreisma I think he's in Vienna now, but there's the whole, yeah, okay, this gets to a very long, this could go on and on and on, but that is what the Veronese is. And in particular, the twisted cubic, which I mentioned, yeah, the twisted cubic, I guess this is why the question was there, is an example.
Yeah. Cool. So, so people were asking what, maybe a little bit about what proj is.
So next time I'll say what proj is. How's that? But let me, actually, no, let me tell you what proj is immediately, and then we'll worry about later why it makes, but then you may wonder why I'm waiting a week to do it. So let's say you have a graded ring, and let's talk about things that are like varieties. So let's say it's got a
oh, by the way, this answers, okay, so there's another question that you are already answering. So Emily asked, is there a notational difference between, how do you distinguish between rings and graded rings? And initially I'd said no, but then now that you're writing this is something that some people do to distinguish a graded ring, is they write that little bullet down there, and that's to indicate that there's a bunch of pieces. Right. Yeah, exactly.
Exactly.
So yeah, graded rings are a direct sum. Yeah, exactly. What he's writing right now.
Yeah. So that's, yeah, exactly. I think, and that's useful. Yeah, no, I do think, and behind Emily's question is like, wise notation tells you, avoids misunderstanding. So yeah, I think that's why, yeah. So the dot is a useful thing to do. Although of course there's no room for a dot here. And there's an implicit grading, but you just are.
Yeah, and always implicit in this is that the ideal here is a homogeneous ideal.
And you may ask, what is a homogeneous ideal? And the answer is, well, what you think it is. But you may think one of several things. You might think that maybe it's generated by homogeneous things, and you'd be right. Or you might think that all the elements are homogeneous, and that's not right. But you might think at least that it's sort of that it's to know whether something in it is in, if you want to check when something's in it, you just need to check each of the graded pieces separately. So there is a nice, there's a definition in the notes, and it's essentially what you think it is.
Yeah.
But let's say for now
It's going to come up again. Yeah, probably.
And okay, so here's what it basically, here's the definition of proj. So I'll tell you, so I want to do this in very big generality.
Well, maybe you can say what is, like, what are you even doing? Like,
okay. So it's okay. So spec is going to take a ring and turn it into an affine scheme, or an M spec will turn a variety. What does proj do? It's going to take a graded ring and turn it into a scheme. And that's and why would you do that? It's because actually this is something where the idea is you think about things in projective space long before algebraic geometry in its modern form was defined. And so that's why it's a natural thing to do. It's more so how do you do it? Well, projective space, you defined it by gluing a bunch of things together. And so now I'll tell you how to get it by gluing a bunch of things together. And now the thing which is not going to be, because I'm just answering a question and I'll do it in 30 seconds, and therefore you can't expect understanding, but you might hope for a precise definition, which is in the case of projective space, you might remember, well, I hope you remember that you had this thing which is, for P2, from the graded ring, you produced this ungraded thing. So what did you do? So I'll have as an open subset. So let me pick a degree 1, I'll put a dot there, element, U, which might be X naught in this example. And now I will tell you an affine scheme. So what I want to do is sort of use U to make everything, get rid of the homogeneity to get rid of things. So I'll take the ring, and I guess I'm going to invert U, and it's still graded. And now the graded ring had only non-negatively graded pieces. And now I've got this negatively graded piece. So then I'm going to take the 0th graded piece of that and take spec of it. And so that's the
building block. Yeah.
What's that?
Oh, building block. That's the.
Yes, exactly. That's my building block. And actually, now I can say forget degree 1. I can use any degree, and that'll still make sense. And now each of these two things are in what's the intersection of two of these things? Well, this is going to be, if that's where X naught doesn't vanish, then it's just like it's like a projective version of a distinguished open set where you take S naught. I think I'll deliberately show you terrible notation because I despise it. So what I said is you take your graded ring, you invert U, and you take the 0th graded piece. And the great thing about this is there are 3 subscripts and they mean different things, 3 different things. So that's your symbol. Does it remind you it's a graded ring? There is U inverting U, and there's the 0th graded piece. But then the intersection of 2 of them is going to be just like, is going to be spec of S dot UV dot 0. And so now you're ready to use that thing about gluing together ring spaces. And so if these things, I told you, I say glue these, take these guys, glue them together. How? Using these. Check the triple intersection, which will involve, as you might guess, UVW, do the triple intersection thing, and you will define proj, and then I could say, I'm done. You know what proj is. So, and then you may want to have some hypotheses on the graded ring to make it be reasonable. But that is the definition. So, but I don't know if, good. I answered the question without actually being helpful. That's.
Yeah. So Jonathan brought up another point too, is that there's kind of a relationship between gradings in GM actions. And I don't know if we want to talk about.
That is, yeah, John.
Maybe later, I don't know.
You would say that. That's because you could take.
I think it's a good question. I think it's a great. So I think it leads to a lot of interesting ideas.
It does. Let me say something, but now you can't. So now if you have a graded ring, let's say the graded ring is, you take like a field and you add some stuff and you mod up by some stuff. So you could take spec of it and you could get rid of the origin because this is an n space and these are homogeneous things. And then you've got an action of C star or GM or K star on it. And you can try to take the quotient and you get projective, you get proj of the ring. So that is a true statement. But what does quotient mean? What does, yeah, okay. Even what does quotient mean is not I think, a fair question at this point, given what people know. Yeah.
I think it's kind of neat that the homogeneous primes turn out to be the generic points of the orbits.
That's a good point. It is worth saying that right. So what are the points of these specs? They're kind of, they're things you think you understand, but you want to have the points come from the graded ring. And so, these have lots of prime ideals, but some of them are homogeneous. I don't know, I should put a dot there. And it's exactly as Jonathan, well, almost exactly, that the homogeneous primes are the ones that give you the points of spec, of proj. It's not quite true because some end up disappearing. They become irrelevant. Like, for example, for P2, how I picture, actually, this is a good excuse to, an important concept, which is when I see this, I picture a 3-space, of course. And that's my picture of spec of it. And then what's proj of it? It's going to be the line, like projective space, it should be lines through the origin in 3-space. So there should be something like at infinity. This is another reason why I draw, well, that's P2. I draw P2 as the surface of a sphere. That you should be able to sort of compactify that and have the plane at infinity. And you should be able to glue this on if you know about like R3 union RP2 should be, in an appropriate sense, this is not the right way to say it, RP3. And so there should be some notion. And similarly, if you take like a conic in P2, that you should picture that as the conic's in P2, so it's way off. You can't see it because it's off screen. That is way off at infinity. There's a conic, and there should be a cone over it, which connects it to the origin. And then we can picture it as an honest cone. And somehow the idea of saying a conic x squared plus y squared equals z squared in 3-space, that should correspond to, we should think a cone, and we should also think about it as being just a conic section at infinity. So there's this dictionary between sort of the affine cone, which is the spec of it. There's the proj of it, and then there's the projective cone. So this statement here generalizes into proj, the projective cone, which is, I'm not going to say what it is yet. It's, you take proj of the graded ring, where you add a bonus variable of degree 1. That's going to be equal to the disjoint union of the spec and the proj. And that makes this thing more precise and says what it means. And even more so, this combined space is a single variety or scheme. And then the thing at infinity is cut out by a single equation locally. It's something you can, this is just sort of a very, I guess in mathematics, in certain parts of at least geometry, it's a common thing to understand spaces by how things behave near infinity or at infinity. And so you can study, and vice versa, some holomorphy, I don't know what people call that. Great, okay, so that now I've wandered and said enough random things that maybe I should just be quiet or follow up.
I think it was great. So there's another question, but going back to this flatness. So someone said, what's the relationship between flatness and Tor?
And Tor?
Tor.
Okay, that's like great. So that's a leading question. So I guess you can't ask that without knowing the answer, I almost feel. But Tor, so I'll say, what is Tor? Okay, so people should know what Tor is. I shouldn't have put the one up there anyway. Shouldn't exactly know what Tor is, but it measures, well, some people obviously do, but it measures the failure of exactness of tensoring. And flatness is about exactness of tensoring. So you should guess that if something's flat, all the Tors should be 0. And that is true. And then the converse is also true, said, and there are many, many ways you can say that. Some are really easy. If, for example, you know, for people who know what these things are, if you're given M and all higher Tors are 0, then very cheaply M is flat. And that's like your dumbest thing. But then you could check more and more special N's. It turns out you can work out, you could do things like this, or There's something called the local criterion for flatness, which is a truly magical statement.
There's the bear.
What's that?
I think the bear has a theorem where you can like check it for ideals.
Yep, that's right. Oh, is that Bear? Who is that? And so there's around 5 or 6 of them, and they are all really, there's for over discrete valuation ring. There's a really easy one for curves. And so essentially, there are lots of different ways of testing for it, which often are useful ways of discovering that flatness has these magical properties. Yeah. One thing I'll say briefly is there's a proof of the local criterion for flatness that I was not aware of until a couple of months ago. So Arthur Ogus, actually he said it, I asked him about it, and it turned out no one really paid attention to this. It was his first published paper, and it's in the middle of it, and it's an elementary, it's way easier than any proof I've known before. That I'd known before. I make no claims of others, but I at least browsed around a fair bit beforehand. Before discovering this. So I think it's slick, and it has the notion of a half exact functor comes up. So maybe I'll if we talk about flatness eventually, I would certainly give that just because.
Okay, so here's the Ogus has this local. I didn't know about this. Yeah, cool. So you were talking about M being the kernel of this exact sequence, right?
Right.
But then, and so you said something about that this process can keep going, and someone brought up, someone asked what check cohomology was.
So
I don't know if, yeah.
Well, actually, I think we might. I'm thinking of doing check cohomology and in a few weeks. So, okay. Which is a little bit aggressive and ambitious, but I will. Okay, but let me give you the 3-minute spiel about it right now, which is, let me see what, okay, great, okay. So people who know about check homology will be upset with what I'm about to say, because in the cases I will talk about, it's super easy and way easier than it is elsewhere. So, because in the case of a variety, say, or a scheme, what do we need for this to, so let's say we have a scheme where we have this, or a variety where you can cover it with finitely many affines. And let's say that even better, the affines, the intersection of 2 affines is affine. And that means that you have this cover of X by finite number of things, and all the overlaps, there's like a finite amount of things in the overlaps too. And you can make the check complex, which says that when you take F of, let's say these affines are U1 through UN, you can take the sections over each of these open sets, sections over the pairwise intersections. And this should look suspiciously like, right, so this should look very suspiciously like what we've been talking about. And then you can take the cohomology of this, and then you get the cohomology of that sheaf. Now let me say where I'm lying and not lying. So what kind of sheaf? I'm talking about sheaves that come from modules. These are quasi-coherent sheaves. And then you also might think I'm lying, because if you know check cohomology, you have to take limits over various things to make them all work. Now here you don't, because this cover is so nice. You should think of affines as being contractible from the point of view of modules, which is secretly maybe where that question came from. That like the higher cohomology of, when you do this to modules, you get 0 for higher cohomology. And so if they're kind of contractible, and the pairwise intersections of affines is also contractible in a sense, then you should not be surprised that you can do check cohomology by taking this one fixed cover. And then, for example, cohomology of projective space, we already have these nice covers, which are these standard open sets we've talked about, and you could just by hand work out the cohomology of projective space. And that is actually how it is done. You can't actually compute anything without doing something by hand to start off your theory.
All right. So one question someone asked is, what would you have named flatness if you could?
Exact. I think I would call it exact.
Exact.
Like an exact module, an exact morphism. I'd want the same name for the morphism in the module. So I think exact seems to be the best. That's somehow where it interferes. It sort of and then you could ask, why does a nice family mean exact? And then that I feel like you could then answer. I could make a case for.
Yeah. So okay. So I have another question that I wrote down was, do we want so so in the definition of localization, right, for an arbitrary multiplicatively closed set, there's an extra piece that some people, I think some first-time learners maybe ignore, is that when two fractions are equal, right, that you multiply times an extra element, right? So yeah. So what is the definition? Yeah, let's write this down.
Right.
I just wanted to write down this observation because I think a lot of people are used to thinking of localizing at domains, and
Right. So
they don't have to deal with this issue.
Right. And so I mentioned that early, and I think I should mention it again because it's something, this is where you begin to pay the price for. So now I really want to not just work in integral domains because I don't need to. And I should say that when you learn about varieties, many books on varieties assume they're built from integral domains, that they're irreducible varieties. And the reason people do this is to avoid this confusion, I suspect. So if you have a ring and you have a multiplicative subset, and I guess that means that if let me say that 1 should be an S, and if X and Y are, people may disagree on the definition, but I'll stick 1 in S because I just feel like then the product of the two is an S. And then, whoops. So then what are so when I divide, I take, so I'm going to call, I'm going to localize at S. I'm going to allow those in the denominator. So the elements are going to be, whoops, this is as a set. It's going to be things of the form A over S, where the numerator is anything in the ring and the denominator is anything in S. Mm-hmm. And now, except I want to say that A1 over S1 equals A2 over S2 if you would, the first approximation that's true, but you need to toss in that there is another S3.
Yeah, and the proofs are so that you have to do this.
That's the right thing to do. To think like instead of saying why is this there, instead ignore it. Say it's not there and try to prove the result is try to explain why the result is a ring, and you will. And at some point you'll say no, that doesn't work. I need to do something. And if I'm an integral domain, I'm okay. But if I'm not, I need to cancel. You will literally get this equation, and then you want to do that, and you can't if S3 is a 0 to 1. So it's absolutely true. You need to do that, and you have no choice. But the way to think about this is when you first learn about localization, the way you should think about this is when you're small, you learn about the rational numbers. Right? First, you learn about the integers, and then they teach you the positive integers and the negatives. And then they teach you fractions, like 2/3 and 1/4. And you build things with little things like Jonathan probably has in his house to make nilpotents out of. So children don't reach the nilpotent stage until later. And so and then they tell you about fractions, and then they tell you how to add fractions. And then they just tell you this rule about A over B plus C over D equals. And they don't really, there's something that they lied to you about, or that they omitted, which is why does it all hold together? And you only really try to make it hold together when you're in college and you're trying to figure out, and you learn about localization. So that localization is doing nothing more than making precise what you're doing with fractions. And then at first you think, because of the way things work, oh yes, of course it has been integral domain when I try to make it work. But then you realize you can give it up. Give up that, and you have to just edit your definition just a little bit, and it actually is super useful. And then, when you were told you can't divide by 0, now you can, because you made the rules, and you can't divide by 0 because it looked like you couldn't do so consistently. Your mathematics would break, but actually no, it doesn't break. I mean, the ring breaks. You blow it up, and you invert 0, and it becomes a 0 ring. So it's bad things happen, but you can divide by 0. Like, oh yeah, that's like a superpower we have.
No, I mean, like, okay, so if I can recommend an exercise is to like, you should take just the crossing, right, and then localize at x. Say so, like if you take x, y is equal to 0, or you take or you take c of x, y mod this, yeah, exactly, right, and then take this and then localize at x is a good. I think if you've never done this before, to localize at a zero divisor.
And I should say you should guess from the geometry what you're going to get. You should guess that this is.
Yeah.
Do I have that wrong? You're inverting x, so no, sorry, that's wrong. X's.
Yeah, y gets killed. So you show that y is 0 in the, yeah.
And the picture is that you have your union of your two axes, and you're throwing away where x is 0. So I erase it, and I'm left with the x-axis minus 0. So you should expect that, but that's an algebra. I mean, that's an algebra statement.
Yeah.
So now you're ready to.
Yeah.
And the last essential thing to do is that when you take a ring and you're localized just at one element, I should say, then the multiplicative set are just the powers of f. Then it is useful to say that this is not by definition. Since that we already defined the localization, but this is what it is. And you can see when f is a zero divisor. Well, actually, that's a great idea. Yeah, when f is 0, you're modding up by 1, right? So it is indeed killing everything. So as soon as you formally add an inverse of f, you can do it. We just did it, but it forces you to. And this is, I guess, yet another reason why you do not. Yeah, right. This is why the zero ring has to be a ring. There's just no question. The zero ring has to be.
Okay, so the last question I have here is, so someone asked why, so they were getting Meyer-Vitoris vibes from your glueability proof, and I don't know.
I am not qualified to answer that, I think. I've not thought about it. It sounds entirely believable, but I'm not.
Yeah.
Yeah.
I don't know. Okay, so that's all I have.
The things you should get vibes about, the things I get vibes about that I do not understand yet, are simplicial things.
Oh, so there might be, yeah. Do you want to maybe, I don't know if you can do this off the top of your head, but to do the relationship between simplicial sets and things like, I don't know.
Well, that's actually something
complex.
That's what I absolutely cannot do, because that's the thing I want to understand and have never understood properly. Yeah. So this is a place where, and it's not a coincidence, and more than that, simplicial tools are super duper ridiculously useful. So as just an example, all the examples I've been giving are things where you can have affines, they intersect. Things are very simple, and you're very lucky. And if you're not in this very lucky situation, then you need way better tools to package your information. So I think this is a case where I can imagine that we might beg Emily to explain stuff, because this is, I mean, back when I said one should never take a course in category theory, whose words I eat with relish and gusto. Actually, maybe a good second last question is that one. But I really wish I could understand simplicial things, and I should say the thing. But I roughly know what I have to read, which is why I knew of Emily long before. I actually don't know if I actually even can't remember if I met her in person, but I know her writing repeatedly from explaining these things. So yeah. So as to why you should never take category theory as a course, I think most people, I stand by what I meant, which is it's kind of like if you can avoid taking, if you can take category theory and it's the right course, put together in the right way, the answer is yes. And Saunders-McLean is not the right course. And it is true that there's probably like a very small number of people in the world I would want to take, there'd be a reasonable number I would like to take a course from, but a very small number that I would love to take a course from on this topic. And that's because it really needs to be explained. This applies to algebraic geometry too. You have to know why you care and understand in your gut, not the idea of it being very dry versus wet. And again, I'll mentioned at the start of one of Emily's books that somehow the examples of things you can say right out that here are examples of things that become clear. And I think I appreciated things in category theory only when I was older and I had the maturity to say, I wish this sort of thing should be true. And then it is true. Or this thing looked really complicated. No, it's not once you look at it from the right way. So I think it has to be taught in a way that gets across that. And there do not exist very many things that successfully do that. And it is so, okay, so that's, so maybe I'll similarly say that maybe I think I'll offend more people is the commutative algebra course, where I feel like it's better to learn commutative algebra. Well, no, I think commutative algebra you can absolutely learn without any algebraic geometry, but maybe it's the other way around.
It's hard. I think commutative algebra without knowing what's going on, like you don't. Some of these things are so rough if you don't.
But some people think about them completely differently. It is true that modern commutative algebra did come post-Grothendieck. It's not like it came from algebraic geometry or vice versa. They just were born at the same. The modern incarnations were affected by. But I think you can't learn algebraic geometry without learning commutative algebra. I think it's better doing it at the same time, not like I feel like doing them in order is worse than, because then you don't know why you're doing it. Unless you're taken from a real commutative algebraist who's taking things in a, like if things are secretly algebraic geometry and you're not told why, that's bad. If things are really fundamentally, there's a lot of commutative algebra that's fundamentally algebraic. And then there are things that I don't know why they're geometric, but they are like the current, like things that Barghaud and collaborators are working on. I'd say these are commutative algebra results, but he's a geometer, so I don't know what he's doing.
Yeah. All right.
Back to that original question about the Meyer-Vietoris vibes, just a comment. I mean, when you generalize Meyer-Vietoris to more than 2 open sets, it becomes the Czech spectral sequence.
That's great. I feel like I'm getting insight into Meyer-Vietoris. I will also admit that I've semi-forgotten what concept Meyer-Vietoris.
It's Van Kampen for
technology you get when you glue two open, and then you get the intersection.
Okay.
And a co-boundary map. So, and you were writing down the Czech complex for a sheaf.
Yes. Great. So the right generalization of Meyer-Vietoris is also the right generalization of the naive Czech complex I was writing down, which is also the
right.
And then we're getting full on simplicial.
All right. I think that's. Does anyone else have anything else that they want to add? And then, if not, I think then we should adjourn.
Great. Well, thank you all. I guess the things I would say for next week are, other than my promise not being as involved as I would have, not being on Zulip when I would like to be, or there are also new people who are signing up that I will hopefully start to catch up. But please keep self-organizing as much as possible, and then I will hopefully wander into Zulip a fair bit this week. Now that other things are over. Okay, so I will see you. Ring or rated. Yes, context. Yes, context is everything.
All right.
Great. Okay. Thanks a lot, everyone. And we'll. I will. Yeah. That question was there. Jonathan, did you have a?
What was that?
You were about to say, were you saying something?
No, I was just saying thanks.
Great, thanks. And now I lost. Haha.